Now, if you haven't picked up on it by now, you've probably noticed this is going to be a fairly math-heavy class, and that means we are going to be working with exact numerical values. Sometimes we do need to know the exact magnitude and the exact direction of these vectors. So what am I supposed to do if I need to know those exact numbers? And that brings us to our second method for vector addition. Remember, the first one was called the graphical method because we were just making this graphic visual model of it. That's why it's called graphical, because it's a graphic. This is the geometric method for vector addition. Essentially, we're going to be using geometry to figure out what the magnitude and direction of these vectors are. And in this class, we're going to be applying the geometric to three different configurations of vectors. Three different ways that these vectors essentially are relating to each other in terms of their direction. The first configuration is going to be something like this, where the vectors are parallel to each other. We call these parallel vectors because they're making essentially parallel lines. These don't have to be up and down. They could be left and right. They're just pointing along the same axes. These are parallel to each other. We can also have vectors that are perpendicular to each other. So notice these two vectors make a right angle to each other. So if you remember from geometry, that means they are perpendicular to each other. So we can also do perpendicular vectors. And then this final vector, when they are neither parallel nor perpendicular, when they are making this angle with each other that is not 90 degrees, these are called skew vectors. If you remember all the way back to geometry, these were called skew lines when they do not intersect at a right angle. So these are called skew vectors. Now for this video right here in our first unit, we are just going to be focusing on adding these two types of vectors together, parallel and perpendicular vectors. That's going to be the skill we are focusing on. In future units, we are going to be focusing on handling these skew vectors. It gets a little complicated with these angles, but don't worry about those yet. The purpose of this video is to be able to add parallel vectors and perpendicular vectors together using this geometric method. So as the name implies, this geometric method is going to involve use of skills from your geometry course. We're going to be looking at these line segments and these shapes to try to figure out what the resulting magnitude is. And it does require geometry. So what we're going to quickly do, because it might have been a couple years since some of you guys have taken geometry, we're going to do a quick little pre-test just to see if your geometry skills are where they need to be. So I have three different graphics here. Each one is different. What I want you guys to do, look at the given information, think back to geometry, and find the value for x in each of these situations. Some of them will be pretty quick. This last one down here might be a little tricky, but I'm going to give you guys about 20 seconds. Look at these and figure out what is the value of x in all three of these situations. If you need some more time, definitely pause the video, but hopefully these were just a quick review of things from geometry. So for this one, if we have a line segment of 12 and 3, this value of x represents the whole thing, 12 plus 3, hopefully you got 15. Over here, this one's a little bit more of a puzzle, but we know the whole thing is 10, part of it is 6, so the remaining one has to be 10 minus 6, or 4. Essentially we want 6 plus 4 to equal 10. Now, this last one, you might have need to pull out your calculator for. You might have noticed that these make a right triangle, or you could have made a nice reasonable assumption that these make a right triangle. So you can use the Pythagorean theorem, a squared plus b squared equals c squared, in order to figure out the length of this hypotenuse. This one is also a special right triangle, 3, 4, 5. The hypotenuse of this is just going to be 5. So if you could do all of these maths, if you could figure out the answer to all three of these, congratulations. You already know how to do the geometric method. You have all the math skills that you need to do the geometric method. If any of these were a little bit confusing, definitely reach out to me and we can go over some of the geometry that you might need to handle this math. So using the geometric method to add two vectors together is actually very similar to using the graphical method to adding vectors together. You're going to start with the same process. We're going to start our examples with vectors that are, again, parallel to each other. They're essentially pointing along the same axis. The first thing you're going to do, let's say we want to add this blue vector of 8 to this yellow vector of 7. Your first step is the same first step as before. You're going to place them in head to tail configuration. So I want to put the tail of the second vector at the head of the first one. So I'm going to do that right here. Then, once you have all your vectors in head to tail configuration, you again need to draw your resultant. That is going to start here and end here. And again, it is a vector from start to end. Pretend that's a straight line. And this is going to be our resultant vector. This is exactly what we did with our graphical method. But from here, you might notice now we have enough information. This is simple enough that we can figure out the magnitude of this resultant. If it is going this length of 8 and this length of 7, the resultant has to be 15, just 8 plus 7. So the magnitude of our vector is 15. But remember, the resultant is a vector, and vectors are not complete without a direction. So we also do need to define the direction. I think right now, 15 to the right is going to be a good enough description. Notice this arrow is pointing to the right. It is not 15 to the left, it's 15 to the right. So I think that's a good description. Again, you can also use positive x if you want to be a little more general because it is pointing along the positive x-axis. The big thing to keep in mind, you need this direction for your resultant. The resultant is a vector. We can do the same thing with this example on the right. Again, we're adding 8 and 7, but notice the directions are a little bit different. So what, again, we're going to do, we're going to take them and put them in head to tail configuration. So I move this 7 so that they are in head to tail configuration. You can draw them right on top of each other, but I like to draw them slightly offset just so you can visualize. So now we need our resultant. It's going to start at the tail and end at the head. So notice the direction I am drawing this arrow. I am drawing it down. So now, just using our basic geometry, we just need to figure out the magnitude of this resultant. We have a full 8 down, we go up 7, so the magnitude is going to be 1. But remember, we need a direction. Look at the direction of the arrow, 1 in the negative y direction. Or again, you could say down if you want, but you do need to communicate that this arrow is pointing down. One thing I just want to point out, notice we added two vectors, 8 plus 7, 8 plus 7, but the results were very different depending on the direction of those vectors. And that's why vector directions are so important. 8 plus 7 is not always 15. Sometimes it's 1. So keep that in mind. So when the vectors are perpendicular, it's going to get slightly more complicated, but keep in mind we are still going to be following the same basic steps. So in this example, we're going to add 7 down to 10 to the left. These vectors are, notice, perpendicular to each other. So our first step, we are going to again put them in head to tail configuration. So I'm going to move one of these vectors. So again, the head of one vector is with the tail to the other. When I do this, I can now draw the resultant from start right here all the way to the finish. And here is our resultant vector. But you might automatically notice, okay, this is going to be a little bit more difficult to figure out because it's not in a straight line and it's at this weird angle. But that's okay because if you notice, the shape that this makes will be very familiar. When we are adding perpendicular vectors, they're going to form a right triangle with that resultant. As long as they're all perpendicular, your two vectors you add together will be these two legs of the right triangle, and then the resultant will be the hypotenuse. And if you remember back from geometry, we can handle right triangles with ease. They're not that difficult. So we have this right triangle, and we need to define the magnitude and the direction. For the magnitude for perpendicular directions, you're always going to use the Pythagorean theorem, a squared plus b squared equals c squared. So one of my legs, 10 squared plus 7 squared equals c squared, which is the resultant. So I'm just going to write r squared. Now I can solve this. 100 plus 49 equals the resultant squared. So 149 equals the resultant squared. Now you got to pull out your calculator, take the square root of 149, and you'll get 12.2. So this is going to be the magnitude. The length of this resultant is 12.2. But again, remember, our vector definition is not complete without the direction. So how can I figure out what direction this is pointing in? Essentially, what is this angle right here? In order to figure out the direction, we are going to use our good friend SOHCAHTOA. If you do not remember your right angle trig, sine, cosine, tangent, I will link a supplementary video in the extra resources for this lesson, but we're just going to use trig in order to figure this out. We can relate this angle to the lengths of these sides. I'm going to use tangent because if you remember, the tangent of an angle is going to be equal to the opposite side over the adjacent side. I like using tangent for these right triangle additions because we already know what the opposite and the adjacent sides are. Those have been given to us. If we use either sine or cosine, we're going to have to use the hypotenuse in our trigonometry. And if we made a mistake calculating the hypotenuse, that mistake is going to carry on into the direction. So I like to use tangent. So we know the tangent of this angle that I marked in the diagram, again, this angle up here, is going to be equal to the opposite side over the adjacent side. So that's going to be 10 over 7. We can solve for this angle theta by doing inverse tan. So inverse tan of 10 over 7. And again, you have to pull out your calculator, but when you do this math, make sure your calculator is in degrees. We're going to get 55 degrees. All right, we're doing geometry, so we want our numbers in degrees, not radians. So now we have a magnitude and we have a direction. Magnitude of 12.2 at 55 degrees. Now, you might say 55 degrees is kind of vague. 55 degrees could easily be in quadrant 1. So when you are communicating magnitude and direction, you pretty much have two options. You can do it again visually. So you can say this is pointing down and to the right, has a magnitude of 12.2, and then you can indicate this angle here is 55 degrees. If you want to do it graphically, just make sure you're clearly indicating where this angle is in reference to. This is in reference to the negative y-axis, not the positive x-axis. But if you want to represent it in our second way using words, then you need to be a little more clear. If you're using words, I would use the unit circle as your way to communicate. And I would then, if it's the unit circle, then you have to figure out what this full angle is here. Remember, the unit circle always uses positive x as 0 degrees. But you can figure that out. It's going to be 215 degrees. I just subtracted 55 from 270. This is also saying the exact same thing. When you're doing it in words, though, I recommend you use the unit circle just because it's really clear. But if you want to use a diagram, it communicates the exact same information. You just need to choose one and be consistent. All right, so to finish off this video, here's a last example I want you to do. We're going to add two vectors together, but we're going to kind of go through the full method. You have not the vectors drawn out for you, but the vectors being given to you using words. So I want you guys to pause the video and try to add a vector of 10 meters to the north to 15 meters to the east. Give me a full result in magnitude and direction using the methods we've shown. So pause the video and I will go over the answer once you're done. So since these vectors were given to us in words, I highly recommend you draw them out first. So we have 10 meters to the north, so I'm going to draw that up because this seems to be using standard north, south, east, west. So I'm going to draw 10 meters to the north. Then the second vector is 15 meters to the east. And don't forget to draw the 15 meter one larger than the 10 one because the magnitude is greater. This is the first time we're using units with our vectors. Make sure you do include the units because units are important. So to add these together, I'm going to place them in head to tail configuration. So I'm going to move that 15 meter right next to that 10 meter. Now, when you're just drawing these out, you obviously can't move around what you draw on the piece of paper. You can just draw them straight in head to tail configuration. Then once I have them in head to tail configuration, I'm going to draw the resultant, again from start to finish, and this is going to be our resultant R. So my next step is to figure out the magnitude of this resultant. And since these were perpendicular vectors, I can use the Pythagorean theorem, a squared plus b squared equals c squared. I'm going to do this with the units following through. I'm going to keep all the units just to show you how the units work out. Again, anytime you write down a physical quantity, make sure you're tagging the units onto it. So I'm going to do 10 meters squared plus 15 meters squared is going to be equal to my resultant squared. So 10 meters squared will give us 100 meters squared. Turns out those units also need to be squared because we have 10 meters times 10 meters. Those units will be meters times meters. Plus 15 meters squared gives us 225, again, meters squared. Don't forget your units, equal to r squared. Now I can add these together. 100 meters squared plus 225 meters squared is going to give us 325 meters squared, equal to our resultant squared. And now pull out your calculator, take the square root of 325. You're going to get 18 and a little bit of decimal places, but it's approximately 18. And then we're also going to square root meters squared. The square root of meters squared is meters. So the magnitude of our resultant is 18 meters. Now, you probably just realized, okay, well, of course it's going to be in meters in the end because I'm adding meters to meters, but I always like us to just get into the habit of following through with the units. I don't like it when units magically appear at the end because you're kind of making a guess as to what the units would be, but this proves to us that in the end, even though we're squaring and taking the square root, we do end up back at meters. So the magnitude is going to be 18 meters. Next, I have to figure out the direction. I'm going to find this angle here. I'm going to use tangent for that. So the tangent of this angle here is going to be the opposite side, 15 meters, over the adjacent side, 10 meters. Those units cancel out. So theta is going to be the inverse tangent of 15 over 10. This is a good thing to check because when you're using tangent, you actually can't have units here. It's a ratio, so it's nice to check that those units are going to cancel out. And when you plug this into your calculator, again in degrees, you're going to get 56.3 degrees. So that's going to be this angle right here. Again, if you are representing it using a diagram, I'll do it in this space here. You can do 18 meters. And keep in mind which angle we did find. It was this one right here. Make sure you are labeling the correct angle. It was this upper angle here. That is a fine way to communicate it. But again, if you wanted to use words, I would use the unit circle. So that is using this angle here. It's going to be the complementary angle to 56.3 degrees. So pull out your calculator. That's going to be 33.7 degrees using the unit circle definition. But again, whether you use 56.3 or 33.7, it is still communicating exactly the same information. You're just using a different point of reference. You're either using the unit circle or you're using this angle you have drawn in your diagram. So in summary, we talked about vector addition, adding vectors together to get this resultant. The big thing you have to remember is that the resultant is a vector. It's the vector result of this vector addition, so make sure you are stating both magnitude and direction to have a complete definition of the result. If you want to find the actual magnitude and direction for this vector, you do need to use the geometric method using the Pythagorean theorem and then using tangent, cosine, sine in order to find the magnitude and the direction. And again, you can either express that magnitude and direction with a diagram, so that's perfectly fine, label the magnitude, and then label the direction. Make sure you are showing that direction clearly in the diagram, or you can do it using words, and just keep in mind if you're doing it using words, that direction should be referenced to the unit circle, just because that is universal.